And now in this lecture we'll answer on two questions. In the first question we find out the area of this rectangle ABCD, and in the second question we'll find out the area of this grain shape. So we start with the first question. In the drawing we have rectangle ABCD. Inside this rectangle we have this semicircle. This is called PA, that is equals to 6 units in its length. This is considered PC, that is equals to 5 units. Again, our mission is to find out the area of this rectangle ABCD. So first of all those four angles inside rectangle ABCD are right angles. So this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. In the next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. We define the touching point of the semicircle with side AB of rectangle ABCD. This point is point E. And we define the point of tendency of tangent DC with this semicircle. This point is point M. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle. This is equal to x units in its length according to our definition. Likewise, OE is also the radius of this semicircle. This is equal to x. We join points O and M together by a straight line. OM is of course the radius of this semicircle. Is equal to x. And because of the fact that the radius of M that is equal to x, the radius of M is drawn to point M. That is the point of tendency of tangent DC with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. By doing this construction, we're going to do the small polygonal DAOM. Inside this small polygonal DAOM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, it turns out it must be equal to 360 degrees according to the rule that says that the sum of the angles in any polygonal is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small polygonal DMOA, we have 4 right angles. And according to rule 5, any polygonal that has 4 right angles must be at least a right angle if not a square. So we relate to this polygonal DMOA as right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle DMO, side MO must be equal to the opposite side DA. But MO is x, therefore the opposite side DA must be also equal to x units in its length. Likewise, the opposite sides of the big rectangle ABCD must be also equal to each other. That is to say, side DA must be equal to the opposite side CB. But DA is x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we join points E and P together by a straight line. By joining points A and E and P, we get a triangle APE. This is triangle APE. peripheral angle APE subtend on AE, that is the diameter of this semicircle, and according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in each side. Therefore, peripheral angle APE is equal to 90 degrees. So, repeat quickly rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees. In the moment we have a circle, AB is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of this circle, and therefore peripheral angle ACB is equal to 90 degrees in size. Actually, we already implemented rule 7 in our drawing. In our drawing, this is peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and therefore peripheral angle APE is equal to 90 degrees in size according to rule 7. Okay, so in the next step, we'll define this angle as alpha, and we'll focus on the right triangle APE. On the right triangle APE, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Y equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to 90 degrees, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, we prove that the big right triangle ABC is similar to this small right triangle, triangle APE. Okay, again, we prove that the big right triangle ABC is similar to this small right triangle APE. two right triangles are similar to each other. First of all, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big right triangle ABC, and angle A also belongs to the small right triangle APE. So you can write down that angle A equals to itself is a common angle that belongs to both triangles. So if we relate to this angle A as it is belong to the big right triangle ABC, it will be defined as angle CAB. And angle A equals to itself. So if we relate to angle A as it is belongs to the small right triangle APE, it will be defined as angle PAE. So repeat again. This equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself is a common angle that belongs to both angles. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle CBA. In the big right triangle ABC, and it is equal to this angle, that is actually angle APE. In the right small triangle APE. So repeat again. Angle CBA in the big right triangle ABC equals to angle APE in the small right triangle APE. They are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees on alpha, therefore they are equal to each other. So finally, this is angle ACB in the big right triangle ABC, and it is equal to this angle. This is actually angle AEP. The small right triangle AEP. So repeat again. Angle ACB, the big right triangle ABC, equals to angle AEP in the small right triangle AEP. They are both equal to 90 degrees from alpha, therefore they are equal to each other. So we can prove that all the triangles in the big right triangle ABC are correspondingly equal to all the triangles of this right small triangle APE. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually prove that the right big triangle ABC is similar. This is the sign of similar to the right small triangle AEP according to angle similarity rule. And from the fact that the big right triangle ABC is similar to this small right triangle APE, we derive that the following relationship exists between their sides. We derive that side AP on the right small triangle APE over side AB of the big right triangle ABC is equal to side AE of the small right triangle APE over side AC of the big right triangle ABC. Repeat again. We will derive that side AP of the small right triangle APA over side AB of the big right triangle ABC equals to side AE of the small right triangle APE over side AC of the big right triangle ABC. AP6 according to what is given as a question over AB. AB is the missing side, so we will leave it as it is. And it is equal to AE. AE is the diameter of this semicircle, that is equal to 2x units in its length. It is twice as long as the radius, it is x. So AE is 2x over AC. AC in total equals to 6 plus 5, that is 11. So in total, we should find out that 6 over AB equals to 2x over 11. Here we cross multiply this equation, and we get that 6 times 11 is 66, equals to 2x times AB. So here we will divide this equation by 2, and we get that 66 over 2 is 33, is equal to 2x over x is x. So in total this expression equals to x times AB. So here we divide this equation by x, and we get that AB, the missing side AB, is equal to 33 over x units in its length. So actually, this is the missing side AB, that is equal to 33 over x units in its length. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length is AB, and the width is CB. So in total, the area of rectangle ABCD must be equal to the length AB times the width CB. AB is 33 over x times CB. CB is x. So here x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So if we find out that the area of this rectangle ABCD is equal to 33 square units. And that is the answer to the first question. So we finish with the first question. In the next step, I'll present to you the second question, and we will solve the second question of this lecture. Our mission in this second question is to find out the area of this grain shape. In the drawing, we have square ABCD. This is line 7BP, that is equal to line 7PC. In addition, we know that this is triangle COP, that is equal to 5 square units in its length. Again, our mission is to find out the area of this grain shape. First of all, we define the length the length of this line segment be PSA, and because of the fact that BP equals to PC according to what is given in the equation, PC must be also equal to A units in its length. BC in total is A plus A, that is 2A, therefore AD must be also equal to 2A units in its length because of the fact that all the sides of any square are equal to each other. Those angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as theta, then this angle must be also equal to theta because they are equal to each other according to the rule that I mentioned. We also know that the opposite sides of a square are parallel to each other. So in square ABCD, this square ABCD, side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles, and those alternating angles are located between the parallels AD and BC, and therefore they are equal to each other according to rule 15. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to rule 15. Likewise, those two angles are also defined as alternating angles, and they are located between the same parallels AD and BC, and therefore they must be equal to each other according to rule 15. So if the size of this angle is beta, then the size of this angle must be also equal to beta according to rule 15. So in total we actually found out that the big triangle ADO is similar to the small triangle POC according to angle similarity rule. That is to say, those two angles are both equal to theta, those two angles are both equal to alpha, and those two angles are both equal to beta. So, can I know that the big triangle ADO is similar to this small triangle COP according to angle similarity rule. So, I write it down. The big triangle ADO is similar, this is the sign of similar, to the small triangle COP according to angle similarity rule. Okay. Those two triangles are similar to each other according to angle similarity rule. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 22. According to rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing you have, this is triangle ABC that is similar to this triangle DEF. According to this rule 22, the ratio between the areas of those two triangles, that is to say the area of triangle ABC over the area of triangle EDF, is equal to the square of the ratio of their corresponding sides. Here, side AC is the corresponding side of side DE, likewise side AB is the corresponding side of side DF, and side CB is the corresponding side of side EF. So, AC is the corresponding side of DE. The square of the ratio of those two corresponding sides is of course AC over DE squared. Likewise, AB is the corresponding side of DF, so the ratio between those two corresponding sides is of course AB over DF squared. And finally, CB is the corresponding side of EF, so the square of the ratio of those two corresponding sides is of course CB over EF squared. So the ratio between the areas of those two similar triangles is equal to the square of the ratio of their corresponding sides. So you can actually implement Rule 22 in our drawing. One foot in our drawing. We have already found out that those two triangles are similar to each other according to angle similarity rule. So according to rule 22, the ratio between the areas of those two similar triangles, that is to say, the area of this triangle ADO over the area of this triangle COP, that is of course the ratio of their areas, the ratio between the areas of triangle ADO over the ratio of the area of triangle COP is equal to the square of the ratio of their corresponding sides. Side AD is the corresponding side of side PC. Why side AD is the corresponding side of side PC? Because of the fact that side AD is in front of angle theta, likewise side PC is also in front of angle theta. So side AD is the corresponding side of side PC. The square of the ratio of those two corresponding sides is of course AD over PC squared. So it is AD over PC squared. Repeat again, according to rule 22, the ratio between the areas of those two corresponding sides, that is to say, the area of triangle ADO over the area of triangle COP, is equal to the square of the ratio of their corresponding sides. That is to say, because of the fact that side AD is the corresponding side of side PC, the square of the ratio of those two corresponding sides is of course AD over PC squared. It is equal to AD over PC squared. So this equation is the implementation of rule 22 in our drawing. The area of triangle ADO is unknown, so we leave it as it is. The area of triangle ADO over the area of triangle COP. It is given us the question that the area of this triangle COP is 5 square units. So we substitute the area of triangle COP by 5, and it is equal to AP over PC AD over PC squared. This letter is D. It is AD over PC squared. AD is 2A, PC is A. So it is 2A over A squared. We have A in the numerator and A in the denominator, so A will get cancelled, and after cancelled A we are left only with 2 squared, that is 4. So in total, if we found out that the area of triangle AOD over 5 is equal to 4. So here we will multiply this equation by 5, and finally we get that the area of the big triangle AOD is equal to 4 times 5, 20 square units. So if we found out that the area of this big triangle ADO is equal to 20 square units. Because of the fact that the big triangle ADO is similar to this small triangle COP, the following relationship exists between their sides. Side AD of the big triangle ADO over side PC of the small right triangle POC is equal to side AO of the right triangle ADO over side OC of the small triangle POC. So repeat again, because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of the big triangle ADO over side PC of the small triangle POC is equal to side AO of the big triangle AOD over side OC of the small triangle POC. AD is 2A over PC. PC is A, and it is equal to AO over OC. AO over OC. In this side of the equation, we have A in the numerator and A in the denominator, so A will get cancelled, and we left only with 2. So 2 equals to AO over OC. Here we multiply this equation by OC, and we get that 2 times OC is equal to AO. We define the length of side OC as B, and we substitute OC in this equation by B, and we get that 2 times B equals to AO. That is to say, AO is twice as long as OC. So we found out that if the length of OC is B, then the length of AO is 2B. In the next step, I present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 23. Rule 23 is true in any triangle, so this is triangle ABC that could be in a triangle. In this triangle ABC, if we draw the red line segment AP, we get two parts, two smaller triangles. The red line segment AP divides the big triangle ABC into two small triangles. The first triangle is triangle APB, and the second triangle is triangle APC. This rule 23 talks about the smaller triangles that were created by drawing the red line segment AP in triangle ABC. According to this rule 23, the ratio between the areas of those two triangles is equal to the ratio between their corresponding bases. So the area of this triangle ABP is the base BP times the height edge over 2. Repeat again, the area of triangle ABP is the base BP times the height edge over 2. Likewise, the area of this triangle APC is equals to the base PC times the height that is edge. Both triangles have the same height, that is edge, divided by 2. Repeat again, the area of triangle APC is equals to the base PC times the height edge over 2. And the ratio between the areas of those two triangles is of course equal to the ratio of those two expressions. So the ratio of those two expressions is, we have here edge in the numerator and edge in the denominator, so edge will get cancelled. We have 1/2 in the numerator and 1/2 in the denominator, so 1/2 also will get cancelled, and we have only with P over CP. BP over CP. So in total, we actually found out that the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. Why? Because the base of triangle ABP is BP, and the base of triangle APC is PC. And the ratio between the bases is of course CP, or is BP over PC. But again, the ratio between the areas of those small triangles is equal to the ratio between their corresponding bases, that is actually BP over PC. Okay, so we can actually implement rule 23 in our drawing. One rule in our drawing this is the big right triangle ADC. This is line segment OD that divides the big right triangle ADC into two parts. Or it divides the big right triangle ADC into two smaller triangles. The first small triangle is triangle AOD, and the second small triangle is triangle ODC. Rule 23 talks about those two small triangles that were created by line segment OD. according to rule 23, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. The base of triangle AOD is AO, and the base of triangle DOC is OC. And the ratio between the bases is AO over OC. So in total, according to rule 23, you get that the implementation of rule 23 in this triangle ADO is as follows. The ratio between the areas of those two triangles, that is to say, the area of triangle ADO over the area of triangle DOC, this expression is the ratio between the areas of triangle DOC over the area of triangle DOA or the area of triangle DOC, and that ratio is equal to the ratio between their corresponding bases. The base of triangle DOA is AO, and the base of triangle DOC is OC. So this equation is the implementation of rule 23 in our drawing. So the ratio between the areas of those two small triangles is the area of triangle ADO over the area of triangle DOC, and that ratio equals to the ratio between their corresponding bases. That is actually AO over OC. Okay. The area of triangle ADO is 20 square units. So we substitute the area of triangle DO by 20 over there on this triangle DOC. The area of this triangle DOC is unknown, so we leave it as it is. And it is equal to AO over OC. AO is 2B. Over OC. OC is B. So we have here B in the numerator and B in the denominator, so B will get cancelled, and we have only with 2. So if we found out that 20 over the area of triangle DOC is equal to 2. Here we will multiply this equation by the area of triangle DOC. And we get that 20 equals to 2 times the area of triangle DOC. Here we divide this equation by 2, and finally we get that the area of triangle DOC, the small triangle DOC, is equal to 20 over 2 is 10. So it is equal to 10 square units. So the area of this small triangle DOC is equal to 10 square units in its size. From the drawing, it is very easy to see that the right triangle ABC is congruent to the right triangle ADC according to side rule. So why those two right triangles are congruent to each other? First of all, side AB of triangle ABC is equal to side DC of triangle ADC. Why? Because ABCD is a square and all the sides of square ABCD are equal to each other. So therefore side AB of triangle ABC is equal to side DC of triangle ADC. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC, because ABCD is a square. And finally, side AC is a common side that belongs to both triangles, so we can write down that AC equals to itself is a common side that belongs to both triangles. So in total, we actually found out that the triangle ABC, the right triangle ABC can work to the right triangle ADC according to side rule. So I write it down. We found out that the right triangle ABC congruent, this is the sign of congruent, to the right triangle ADC according to side rule. And from the fact that those two right triangles can point to each other, we derive that they have also the same areas. That is to say, the area of triangle ABC is equal to the area of triangle ADC. So repeating it, we already found out that the triangle ABC can point to triangle ADC, therefore they have also the same areas. That is to say, the area of triangle ABC is equal to the area of triangle ADC. That is again, the area of triangle ABC is equal to the area of triangle ADC. But from the drawings, it's very easy to see that the area of triangle ADC total is equal to 20 plus 10, that is 30 square units. So we can write here that the area of triangle ADC is equal to 30 square units, and from this equation, the area of triangle ABC equals to the area of triangle ADC equals to 30. We will derive that the area of triangle ABC is equal to 30 square units. So we derive that the area of the right triangle ABC is equal to 30 square units from one side, but from the other side, the area of this triangle ABC, if we define the area of this green shape, that is the area that we are looking for in this question, if we define the area of this green shape as x, that is to say, it is equal to x square units according to our definition, then in total the area of this triangle, the right triangle ABC will be equal to x plus 5 square units. So from the other side, the area of the right triangle ABC is also equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We will derive that x plus 5 equals to 30. And from, we subtract 5 from the equation, and we get that x equals to 30 minus 5, that is 25. So in total, we actually found out that the area of this green shape is equals to x is equal to 25 square units. That's all for the second question. So in the next step, I'll summarize the lecture. I'll start with the first question, of course. The first question, our mission is to find out the area of this rectangle ABCD. So, in the drawing we have rectangle ABCD, and we have this semicircle that is inside rectangle ABCD. This is called PA, that is equals to 6 units in its length. This is 973C, this is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. First of all, because of the fact that ABCD is a rectangle, all those 4 angles inside the rectangle ABCD are right angles. In the next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. We define the touching point of this semicircle with side AD of side AB of rectangle ABCD. This point is point E. We define the point of tendency of tangent DC with this semicircle. This point is point M. Point O is the center of this semicircle. Point A is the point of the semicircle itself. Therefore, OA is the radius of this semicircle is equal to x units in its length according to our definition. Likewise, we join OE is also the radius of this semicircle that is equal to x units in its length. We join points O and M together by side 9. OM is also the radius of this semicircle that is equal to x units in its length according to our definition. Because of the fact that the radius OM that is equal to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle, and whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we're going to do the small quadrilateral DMOA. Inside this small quadrilateral DMOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, it must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral DMOA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle and flat square. So we relate to this quadrilateral DMOA as rectangle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So rectangle DMOA, side MO must be equal to the opposite side DA. But MO is x, therefore the opposite side DA must be also equal to x units in its length. Likewise, the opposite sides of the big rectangle ABCD must be also equal to each other. That is to say, side DA must be equal to the opposite side CB. But DA is x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we join points B and E together by side line. By joining points B and E, we get a peripheral angle APE. This peripheral angle APE subtends on AE, that is the diameter of this semicircle, and according to rule 7, any peripheral angle that subtends on the diameter of this circle must be equal to 90 degrees in its size. Therefore, this peripheral angle APE is equal to 90 degrees in its size according to rule 7. In the next step, we define the size of this angle as alpha. So in the right angle APE, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha, according to the same rule that says that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we proved that the big right triangle ABC is similar to this small right triangle APE. Why those two right triangles are similar to each other? First of all, this is angle 8, it is a common angle that belongs to both triangles. So we can write out that angle A equals to itself is a common angle that belongs to both triangles. In addition, we have those two angles that are both equal to 90 degrees, therefore they are equal to each other, and finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So in total, if you found out that all the angles of the big right triangle ABC are correspondingly equal to all the angles of this small right triangle APE. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side AP of the right triangle APE, or side AB of the right big triangle ABC is equal to side AE of the right triangle APE over side AC of the right big triangle ABC. Then again, we derive that side AP of the right small triangle APE over side AB of the big right triangle ABC equals to side AE of the right small triangle APE over side AC of the right big triangle ABC. AP is 6 according to what is given in this equation. AB is the missing sides of millimeters it is, and it is equal to AE. AE is the diameter of this semicircle, that is equal to 2x over AC. AC total equals to 6 plus 5, that is 11. So in total, actually found out that 6 over AB equals to 2x over 11. Here we cross multiply this equation, and finally found out that 6 times 11 is 66, and it is equal to 2x times AB. Here we divided this equation by 2, and finally found out that 66 over 2 is 33, so 33 equals to 2x over 2 is x. So in total, this expression equals to x times AB. In total, we found out that 33 equals to x times AB. Here we divided this equation by x, and finally found out that AB equals to 33 over x. Our mission is to find out the area of this rectangle ABCD. We have to find out the rectangle ABCD. Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is BC. So in total, the area of rectangle ABCD must be equal to AB times CB. AB is 33 over x, and CB is x. So in total, the area of rectangle ABCD must be equal to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled, and the left only will be 33. So in total, we shall find out the area of this rectangle ABCD, that is the area that we are looking for. This question is equal to 33 square units. We finish with the first question. In the next step, I present to you the second question, and we solve the second question of this lecture. Our mission in this second question is to find out the area of this green shape. In the drawing, we have square ABCD. This is square ABCD. This is line segment BP. That is equal to line segment PC. This is triangle POC. That is equal to 5 square units in its size. Again, our mission is to find out the area of this green shape. First of all, we define the length of this line segment BP as A. Therefore, PC must be also equal to A because they are equal to each other. We know that all the sides of a square, any square, are equal to each other. Therefore, BC equals to AD. But BC is 2A, therefore AD must be also equal to 2A units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this angle is theta, then the size of this angle must be also equal to theta because they are equal to each other according to the rules that I mentioned. We also know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles, and they are located between the parallel lines AD and BC. That is to say, AD is parallel to BC. And therefore, those two angles are equal to each other according to rule 15. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to rule 15. Likewise, those two angles are also defined as alternating angles, and they are located between the same parallel lines AD and BC. That is to say, AD is parallel to BC. And because of the fact that those two alternating angles are located between the parallel lines AD and BC, they must be equal to each other according to rule 15. So if the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other according to rule 15. In total, we have found out that the big triangle AOD is similar to this small triangle POC according to angle similarity rule. That is to say, those two angles are both equal to theta, those two angles are both equal to alpha, and those two angles are both equal to beta. And because of the fact that those two triangles are similar to each other, we can implement here rule 22. So I put quickly on rule 22. Rule 22 talks about similar triangles, of course. In the drawing, we have this is triangle ABC that is similar to this triangle DEF. According to rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So here, triangle ABC is similar to triangle DEF. The ratio between the areas of these two triangles is of course the area of triangle ABC over the area of triangle ADF. And that ratio is equal to the square of the ratio of their corresponding sides. What is the square of the ratio of their corresponding sides? Here, side AC is the corresponding sides of side DE, likewise side AB is the corresponding sides of side DF, and finally side CB is the corresponding sides of side DF. So, the square of the ratio of their corresponding sides, here we have side AC is the corresponding sides of side DE. So the square of the ratio of those two corresponding sides is of course AC over DE squared. So the ratio between the areas of the two similar triangles is equal to the square of the ratio of their corresponding sides. Likewise, side AB is the corresponding sides of side DF. The square of the ratio of those two corresponding sides is of course AB over DF squared. And finally, CB is the corresponding side of EF. So the square of the ratio of those two corresponding sides is of course CB over EF squared. Okay, so we can actually implement the new rule in our drawing. Why? Because in our drawing we have already found out that the big triangle AOD is similar to this small triangle COB. Therefore, we can implement here rule 22. According to rule 22, the ratio between the areas of those two similar triangles, that is actually the area of triangle ADO over the area of triangle COP. That is the ratio between the areas of those two similar triangles. That ratio is equal to the ratio of their the square of the ratio of their corresponding sides. Side AD is the corresponding side of side PC. So the square of the ratio of those two corresponding sides is of course AD over PC squared. So in total, we can find out that the area of triangle ADO over the area of triangle COP equals to the square of the ratio of their corresponding sides. That is actually AD over PC squared. So this equation is the implementation of rule 22 in our drawing. The area of triangle ADO is unknown, so we leave it as it is over the area of triangle COP. The area of this triangle COP is equal to 5 square units according to what is given as the equation. So we substitute the area of triangle COP by 5, and it is equal to AD over PC squared. AD is 2A, PC is A. So AD over PC is 2A over A squared. We have A in the numerator and A in the denominator, so A will get cancelled and we left only with 2 squared, that is 4. So in total we can find out that the area of triangle ADO over 5 equals to 4. Here we multiply this equation by 5 and finally found out that the area of the big triangle ADO is equal to 5 times 4, that is 20 square units. And again, the area of this triangle ADO is equal to 20 square units. Because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. That is to say, side AD of triangle ADO over side PC of triangle PCO is equal to side AO of triangle ADO over side OC of triangle POC. Repeat again. Side AD of triangle ADO over side PC of triangle PCO is equal to side AO of triangle ADO over side OC of triangle COP. AD is 2A and PC is A. Again, AD is 2A and PC is A, and it is equal to AO over OC. We have A in the numerator and A in the denominator, so A will get cancelled and we left only with 2. So 2 equals to AO over OC. If we multiply this equation by OC, and we found out that 2 times OC equals to OA. We define the length of side OC as B, so OC equals to B according to our definition. Then we substitute OC by B in this equation and found out that OA equals to 2B. That is to say, if the length of OC is B, then the length of OA is 2B. That is to say, OA is twice as long as OC. In the next step, I presented to you a new rule and we implemented the new rule in our drawing. The new rule is actually rule 23. Repeat again on rule 23. according to rule 23. First of all, rule 23 is true in any triangle. This is triangle ABC that could be any triangle. According to rule 23, if we draw line segment AP, the red line segment AP in triangle ABC, it will divide triangle ABC into two small triangles. It will divide it into two parts, or it will divide it into two smaller triangles. The first small triangle is ABP, and the second small triangle is APC. Rule 23 talks about the smaller triangles that were created by drawing line segment AP in triangle ABC. According to the new rule, the ratio between the areas of those two small triangles is equal to the ratio of their corresponding bases. The area of triangle ABP is the base BP times the height at its edge over 2. Repeat again, the area of triangle ABP is equal to the base BP times the height edge over 2. Likewise, the area of this triangle APC is equal to the base PC times the height at its edge. They have the same height over 2. So it is the base PC times the height edge over 2. The ratio between the areas of those two triangles is of course equal to the ratio between those two expressions. And the ratio of, between those two expressions we have here is this expression. We have edge in the numerator and edge in the denominator, so edge we can cancel. We have 1/2 in the numerator and 1/2 in the denominator, so 1/2 also we can cancel. And we left only with BP over CP. BP is the base of triangle ABP, and PC is the base of triangle APC. So in total, we actually found out that the area of triangle ABP over the area of triangle APC, that is the ratio between the areas of those two small triangles, is equal to the ratio between their bases, that is BP over PC. Okay, so we can actually implement rule 23 in our drawing. Why? Because in our drawing, this is the big line triangle ADC. This is line segment OD that divides the big triangle ADC into two smaller triangles, triangle AOD and triangle OCD. Rule 23 talks about the ratio between the areas of those two smaller triangles is equal to the ratio between their corresponding bases. The base of triangle AOD is AO, and the base of triangle ODC is OC. So the ratio between the corresponding bases is AO over OC. So according to rule 23, says that the ratio between the areas of the two small triangles is the area of triangle ADO over the area of triangle POC. Again, the ratio between the areas of those two small triangles is actually the area of triangle ADO over the area of triangle DOC. That ratio is equal to the ratio between their corresponding bases. The base of triangle DOC is AO, the base of triangle DOC is OC, and the ratio between the two bases is of course AO over OC. The ratio between the two bases is AO over OC. So the ratio between the areas of the two small triangles, that is the area of triangle ADO over the area of triangle DOC, is equal to the ratio between their corresponding bases, that is actually AO over OC. The area of triangle ADO is 20 square units over the area of triangle DOC. The area of triangle DOC is unknown, so we leave it as it is, and it is equal to AO. AO is 2B over OC. OC is B. So in total, AO over OC is 2B over B. So in total, we can find out that 20 over the area of triangle DOC equals to 2B over B. We have B in the numerator and B in the denominator, so B will get cancelled and we left only with 2. So in total, we can find out that 20 over the area of triangle DOC equals to 2. Here we multiply this equation by the area of triangle DOC, and we found out that 20 equals to 2 times the area of triangle DOC. Here we divided this equation by 2 and finally found out that the area of the small triangle DOC equals to 20 over 2, that is 10 square units. The area of this triangle DOC is equal to 10 square units. It is very easy to see from the drawing that the right triangle ABC can go into the right triangle ADC according to side rule. Because of the fact that ABCD is a square, all of its sides are equal to each other. So why those two right angles are similar to each other. First of all, side AB of triangle ABC is equal to side DC of triangle DC because ABCD is a square. Likewise, side BC is equal to of triangle ABC is equal to side AD of triangle ADC for the same reason. And finally, side AC is the common side that belongs to both triangles. So we can write down that side AC equals to itself is the common side that belongs to both triangles. So in total, we actually found out that the area of triangle ABC and that triangle ABC is congruent to triangle ADC according to side rule. And from the fact, so I repeat again, we actually found out that the right triangle ABC congruent, this is the same congruent to the right triangle ADC according to side rule. All the three sides of this right triangle ABC are corresponding equal to all the three sides of this right triangle ADC. And from the fact that those two right triangles congruent to each other, we derive that they are also the same areas. That is to say, the area of triangle ABC is equal to the area of triangle ADC. But from the drawing, it is very easy to see that the area of this triangle ADC in total is equal to 20 plus 10, that is 30 square units. So we can write here that the area of triangle ADC equals to 30 square units, and from this equation, the area of triangle ABC equals to the area of triangle DAC equals to 30 square units. We derive that the area of triangle ABC is also equal to 30 square units. Repeat again, we derive that the area of triangle ABC is also equal to 30 square units from one side, but from the other side, the area of this right triangle ABC, what is the area of triangle ABC from the other side? If we define the area of this green shape as x, that is to say the area of this green shape equals to x square units according to our definition, then in total the area of this right triangle ABC will be equal to x plus 5 square units. So from the other side, the area of this triangle ABC equals to x plus 5 square units. So we can write here that from the other side, the area of this triangle ABC is also equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30, we will derive that x plus 5 equals to 30. Here we subtract 5 from this equation, and finally found out that x equals to 30 minus 5, that is 25 square units. X is the area of this green shape, so in total we found out that the area of this green shape is equal to 25 square units. Okay, thank you very much.